Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Mr. Joe Zhang. Joe got his bachelor degree from USTC, University of Science and Technology in China, in 2003. Then he went to Chinese University of Hong Kong for master. His supervisor is John Liu and Daming Chiu. And after he got a master, he went to Princeton University, and he's now a PhD student, supervised by Jennifer Roxford and Meng Chang. Without further delay, let's hear what he has to say about cooperative content distribution and traffic engineering in an ISP network.
Thanks, Jim. And thanks everyone for coming to this talk. I'm very glad to present my talk here. During the talk, you're free to raise any questions and give me any comments to improve my work. So basically, I'd like to have this talk in two parts. Now for the first part, I'm really presenting this piece of work, which is really recent, and about this cooperation between ISP and content providers. And in the second part of the work, I really would like to grab some time to talk about my ongoing research and research roadmaps that I'm interested in doing peer-assisted live streaming systems. So okay, first talk about the first part. So this work is a collaboration with Ray, who's a postdoc in my group, and also Jennifer and Moon. So nowadays, there are two types of people on the internet today. One is the internet service providers, ISPs. So these people, they deploy the services, providing connectivity to end users. So their main job is to make the decision how to route the packets. So here are a list of the major ISPs in North America. So they are the tier 1 ISPs here. So as I said, their major job is to route packets. And on the other hand, there are another type of people who's got content providers. So they're utilizing the existing connectivity from the ISPs, and they generate and distribute the content to the end users. So nowadays, because of the existence of content providers, so the marginal revenue of the ISPs is getting decreased, because these content providers will directly provide the content to the end users and may gain a larger share of the total revenue from the end users. So here are a list of these possible content providers, like the largest CDN network, Akamai, and all these other kind of peer-to-peer networks. So as you can see, there's a variety of technology used here for content providers, either from this kind of content distribution network-based or peer-to-peer based. But their major job is to decide where to find the content. So this is their main job. So despite the some kind of the economic conflict between the two types of people, now in this talk, we're really trying to see what is the technical tussle between the two types of people. So this picture shows a high-level interaction between the two people here. So from the ISP's perspective, their main job is to do traffic engineering to route the packets. So from their point of view, so they will review the background traffic and all these traffic generated by the content providers as a constant. So they input these parameters and generate the routes. And on the other hand, interestingly, for the content providers, this is kind of a mirror image to each other. So in the content provider's point of view, these routes, the routing, somehow is considered as a constant. And their job is to maximize the user performances by assigning servers or peers to the appropriate users. So the content provider will decide the traffic from the server to end users.
So it just seems like BitTorrent is just so different than Akamai, but you're lumping them together.
Yeah.
Totally.
Yeah, I agree that like this P2P technology is quite different from the server selection I'm talking about here. So in here, mainly like referring the content providers as like Akamai CDNs. Yeah, so this is the major focus of this work.
And YouTube is different on the other way, right? They're just sourcing the content, right? They're not really a CDN or peer-to-peer.
Yeah, but there's some commonalities. Like they also want to replicate the content over many locations, and they choose appropriate servers for the end users.
Right. So they would use CDNs.
Yeah, you can say it's a CDN, but CDN usually refers to Akamai-based. Like they would like to store the web objects, and they use different technologies, but the high-level architecture is kind of similar. Okay. So an interesting point is that the two entities here form a feedback loop. So later, let's see what's going on in this picture. So now, although there's some tussle between the two types of people, but cooperation somehow is possible. Like nowadays, the ISP is trying to deploy their own content services. Like ISP, they're promoting this triple play. You can have the internet access, you have phones, and you also have IPTV. So there stands a chance that the traffic engineering somehow can be jointly optimized with the server selection decision. So this is a good news, which represents a promising direction that the ISP can do. So in this talk, I'm going to talk about the cooperation. What are the possible cooperation models, and how can an ISP to choose between these different models, and how to trade off them. So this is the contribution of our work. So first of all, we asked the question, can we model the current status today? So how can we model the interaction? And is there any efficiency loss? And the second question, after we observe some efficiency loss, then we're trying to probe some possible cooperation models there. Then after we have these models, then naturally we want to choose the best one. So there's always a trade-off between this performance, information exchange, and fairness or architectural complexities. So I'll guide you through these models and see what might be the best model the ISP should choose. So this is the main contribution of this talk, of this work. So here's my outline. First of all, I'll briefly discuss the cooperation models and model the current status, how traffic engineering and server selection is done. Then I'm going to analyze the performance of these models and see their pros and cons. Then I will propose the right solution using of a joint design, using the solution concept called Nash bargaining, and show you some performance evaluations. And finally, I will conclude the talk. Now let's go into the possible cooperation models here. Now, the first model is really no cooperation, which is reflecting the current practice today. So notice that in this picture, so the ISP is doing its own job. Given the traffic matrices, it produces the routes. But from the content provider's point of view, it has no information about the network. So what it observes, the vanilla information that the content provider can get is the end-to-end information. So it either measures the network or do some fancy algorithms to infer the network status. But the end-to-end information is the minimum information that the content provider can directly get from the network. So in this model,
So just Two questions. One is the content provider has multiple ISPs
Yeah.
that needs to be, and the other, they do signal back and forth because the content provider is buying capacity in the data centers of the ISP. So they have to declare how much capacity they need to the ISP.
True. I think the first point is very good. So the content provider may class multiple ISPs. So that makes the scenario more complex. But here, let's now narrow down to the case that when there's only one single ISP, and we only concentrate on the performance issues. And secondly, these content providers, of course, can buy capacity from the ISP. But there are so many content providers, but for some of them, they don't have this kind of separate backbones. So they really have to share the pipes of the ISPs with other traffic.
Oh yeah, they certainly do.
Yeah.
But they buy like, let's say 10 gigs or whatever they buy, and much less in a data center. ISP knows they need to provision for that.
Yeah, so that's why they somehow need to sign a contract, right? Yeah. So in this case, I'm going to talk about, so what kind of, if you have no contract, so what is the best you can do, and why you should have sign some contract like this, and what kind of contract you should have. Yeah, so this is the first model. Remember that in this case, the content provider only has the minimum information. Now let's proceed to the second model. So in this case, suppose the ISP is generous, given all the information to the content providers. This information includes the topology, the capacity, and all the routes. So the content provider can make a better decision to optimize its own network. So in this case, we call it partial cooperation because the content provider is given more visibility of the network. And in this case, we're going to model how the content provider can utilize this information and optimize its performance. So this is the second model.
What is that is given here? The topology?
Yeah, the topology.
The routing?
The routing.
And what about the current link utilizations?
Yes, sure. And the third model is a joint design. So in this case, there are no separate entities there. So we can think of it as a black box here. So in this case, this is a joint design. So given the background traffic matrix and user demand, so it's possible that to optimize the routes and the service selection at the same time. So we call it the cooperative service selection and traffic engineering. So this is a joint design for the third model. So for now, you keep these three models in mind.
In addition to single ISP, you also assume single content provider?
Yes, in this case, yeah. So before going into all these models, I just want to give a quick review of the results I obtained from the study. So to study these models, we really want to evaluate from 4 dimensions. The most important is, of course, the optimality gap. And secondly is how much information exchanged between the two types of people. And third is the fairness, because the objectives of the TE and CSS may be conflicting. So how to trade off the fairness. And the last is the architectural complexity. So the major results here are highlighted here. So as we can see, for the optimality gap, the model 1 with no cooperation has the largest gap, and it can be improved from model 2 to model 3. And model 2 has some special properties that it is optimal in some special cases. But interestingly, you'll see that in model 2, when there's more information, sometimes you get hurt. You're not even doing better than model 1. So this is one of the interesting observations we found. And in the third model, so we propose this joint design, and I'm going to show you how it can be decomposed into still 2 separate jobs. So with some information exchange. And we'll also compare these architectural complexity, say what is the most lightweight loaded for you to do if you want to migrate to another part. So this is the high-level summary of my result.
Optimal for who?
Optimal.
For who?
Optimal for both people. Yeah, so I haven't defined the concept of optimality, but later you'll see. So yeah, so this is also a trade-off curve. So these are the possible operating points on this three-dimensional space with different performance metric. So like in Model 2, it has the least efficiency, but for Model 2, sometimes improves, sometimes does not. And for Model 3, it is optimal, but there may be higher communication cost and architectural complexity. So we really want to find a good operating point on this space. Then I'm going to model the existing status quo. So this will be a quick review of some existing optimization models. Now, first of all, I'll talk about traffic engineering. So for traffic engineering, the major problem is for the network operators to minimize the congestion of the network. So given the traffic matrices on the network, source destination pairs, so the ISP either tune the link weights or solve a multi-community flow to find the best routing decision, like this. So here we assume that they can use a multi-pass routing in this case. So to give a more accurate formulation, so here's the traffic engineering problem. So the first input is the topology and the links and the nodes. And second input is the traffic matrices, which is exactly the load between any pairs of these source and destinations. And we use this variable xij to denote the traffic load from I to j. And the output is the routing. In here, we're not really modeling the current status, like this kind of using link weights. But we're trying to use a more general decision space using the multi-community flow. So here the decision Rijl is the fraction of the total traffic from I to j that is traversing a link L. So here's just an example of the possible solutions of the flow. So we see that they should satisfy the flow conservation here. So now I haven't talked about the objectives of the ISPs. So the objective of the ISP is to minimize congestion. And so they have the objective function here as a sum of all the link cost. So the link cost is a function g of the total traffic on the link, which is denoted as FL. So the cost function is something like this convex non-decreasing function to reflect the goal that ISP don't want to have high link utilization here. So and in the formulation, so here the links should satisfy the capacity constraint, and the second line of the constraint is just the flow conservation. So this is the optimization model. So this is classical, which is not my contribution here. Yes?
So do you consider delay here?
Delay? From the ISP's perspective, to try to avoid link overutilization is the main goal. So delay is not their primary concern.
The SLAs usually say like delay, right? They need to bound the delay for certain customers, right?
Yeah. So by using this objective function, so somehow you automatically try to find shorter paths. Like if you go longer paths, then you see that if you sum over all these links, because the traffic use more links, so the load automatically increases. So this objective goes higher. But this objective function is just its general formulation that is used by ISP to make their routing decision.
ISP is going to care about delivering the content to its customers.
Yeah.
Its broadband eyeballs, essentially.
Yeah,
Not
that's
so
true.
much transit traffic.
Yeah.
Can you distinguish
So I think in this model, I'm not really concerned with this decision. But I think this is the general behavior that ISP does, just do the routing. But of course, there exists a possibility that should consider, especially consider the routing of the subscribe users like the content providers. But here, just assume that they do not differentiate the traffic between the background traffic and the content providers traffic. Okay, that's clear. Okay, so now in here, I'm trying to model the server selection problem. So as I say, assume that in this context, I'm trying to model the case that the content provider can replicate different copies of its content to different servers. So its main problem is to assign the best server for every end users. So for example, the ISP wants to, the content provider wants to optimize the average user perceived performance, like the delay or other the transmission rate. So for example, we care about the latency here. So in a special case, the ISP, the content provider, can do load balancing. So here, the end user actually is not the normal end user. It's maybe an edge router that aggregates the traffic from all the end users behind the local ISP. So it's going to decide for every this edge router, what is the load to each of the servers. So this is the decision space for the content provider. So for the problem, the input is still. So suppose now the content provider has the full information. So it has the input of the topology, and has the routing, and all these kind of user demand. User demand is really the rate you have to satisfy for each of the end users. So its decision variable is here, the server user rate. We use this ST to denote the server and destination and end user. So this is really the decision variable for the content providers. And it has to satisfy the constraint that it meets the demand. So here I give a optimization model for the server selection problem. Given the assumption that it has the complete information, which is really the model 2 here. So in this case, suppose the content provider wants to optimize the user latency. But if you rewrite this objective, it can be formulated as a sum of the cost, link cost. But the cost function is different from the ISP's link cost function. So here, this is the user cost function, and this variable denotes the content provider's traffic on the link. And here is the total traffic, includes the content providers and the background traffic, and which satisfy the capacity constraint and meets the demand here. So to give you a better understanding of what this function may like, say, if you want to optimize the average delay of all users, so a simple way is to do this weighted delay. So D is the delay latency function of the link, and here is the amount of CP's traffic on the link. So by using this objective function, it maps to the average delay of all the users. So this is one of the example we'll be considering here. So is that clear about this model? Okay.
We're going to tie it to the charging model?
I'm not reflecting charging here, yeah, the economics here. So, but if you go to the first model for the content provider, it does not have the complete information. So we assume that the CP only observes the end-to-end cost, like the end-to-end latency, which is pretty much like the what the CDN Akamai is doing. Like it uses DNS to choose the closest server to each of the users. So we're building this model reflecting the current practice in some sense. So in this case, the server selection choice is called greedy, which means that I always choose the server with the smallest latency. And you can do load balancing whenever possible. So that basically means that if you can use multiple servers, then these servers will have the same latency. Otherwise, you can switch some traffic to a better server. So this is theoretical similar to so-called selfish routing, which can achieve this wardrobe equilibrium, which means that, okay, by giving this model, there's no self-oscillation from the CP's perspective. You can study the equilibrium point of the CP. And you can show that this greedy server selection is minimizing like this function, which is not relevant to the context here, but just give it here. You can plug into the optimization model here. Then it is modeling the greedy server selection behavior.
That's D.
D is the latency function, link delay function. Yeah, so this is not my work. So this is some theoretical work. Yeah.
So not part of this problem is where to put your servers, right?
Yeah. So I'm not modeling the server placement decision because it may happen in a very different time scale compared to the traffic engineering. Because you deploy your servers, yeah, right before you start your business. So yeah, that might be a very important problem. But in here, we're just trying to model that. Okay, we're not trying to model how content provider can do from a clean state, but rather what the content providers and ISP is experiencing in the current status quo, and how can you improve them. So of course, maybe you can do some replace servers using some virtualization, but that might be a different model. But here, just assume that the content provider is the decision variable is the server selection. Okay. Yes.
Yeah, I'm not sure I understand this equilibrium. So this equilibrium may say that the content providers does their own adjustment, and this all the traffic changes gets feedback to the ISPs, right? And ISPs do their own mirroring, and you achieve this equilibrium.
Yeah. So I suppose that the equilibrium point is achieved before the ISP take another round of action. So this is an assumption. Yeah. So that is of course, when you do this greedy server selection, there might be some oscillations, but we assume that it converges to a stable point before the ISP takes another action. Okay. So yeah, I'll see how to model the interactions by using a two-player game and how they solve the game later.
Wait a second. So assume the equilibrium is achieved before the ISP do anything.
Yeah.
So this is purely based on the content provider's adjustment.
Yeah. So okay, so after finishing modeling the current practice, so now we're going to analyze the performance of the model 1 and model 2 when the traffic engineering and server selection are two separate problems. So we're going to find a set of good news and bad news. So to study their interaction, because the two problems are separate and they have this kind of feedback loop. So game theory is a natural tool to study their behaviors. So in this setting, we formulate it as a two-player strategic game. So the two players are ISP and CP, and their action set is the routing and the server selection decision. And the utility functions is just the negative of the objectives of TE and SS. So we consider a special gameplay, and which is like the two players will iteratively optimize the best response, using the best response, which means that in each round, one player will fully solve their problem before the other user takes action. So this is the way how the game is simulated. Okay. So in this game setting, so we're going to study their properties. So first of all, I'm going to bring you some good news about this. Now, the first theorem shows that the strategic game has an equilibrium point for both Model 1 and Model 2. So this is a good news, which basically means that, okay, it is possible for the two parties to settle down to a stable point and there be no oscillation. And it is this stable point that you can study at which you can study the benchmark performance. So this basically means that, okay, this provides a good a way to study their performances. Otherwise, if the performance is always oscillating, it will be hard for us to track the benchmark performance. But the Nash equilibrium may not be unique, which is very problematic, as I will show later. And secondly, it may not be achieved through iterative optimization. This is not guaranteed from the theory. It just says the theory just says the existence. So we showed this the achievability of the equilibrium point using simulation. In most of the cases, it converges. So this is about the stability of this interaction model. This is the first news I bring to you.
This is about the Nash equilibrium. If it's not unique and you have multiple equilibrium points,
Yeah.
are you saying that they're equivalent, or
They're
one
not.
may be- one may be
Unfortunately,
better?
they're not.
So one may be better than the others.
Yeah, so from the TE's perspective, from ISP's perspective, usually the objective value is the same, but for the CP, it may not. So, yeah.
Is this different from like hill climbing optimization?
Yeah, it's kind of hill climbing. Yeah. So when you solve the game, although you don't have a synergistic objective function, but you're optimizing through different variables. Yeah. So interestingly, so this is the second news, which is good, which is global optimality on the same objective, which is just go back to your question about this hill climbing algorithm. So when they have the same objective function, then you can see that they're actually solving this optimization problem. This game is solving this problem. So they have two variables. One is the routing, one is the server selection. So they optimize iteratively over the two variables. And think about this. This is not a good formulation, because for this game formulation, it is not in a convex form. So you're not guaranteed that this kind of hill climbing algorithm can achieve this optimality. So instead, we look at this global optimization problem. So in this case, they have the same objective, but we relax the decision space, which is I use the XSTL here, which denotes I can directly assign the exact amount of traffic on the link rather than the percentage of the traffic. So you can simply think of this new variable as the product of the two variables here. But of course, by using this, you have a broader decision space, and we called this optimal value of this problem as global optimality. So the natural question is, can this kind of game formulation achieve this global optimality? So the answer is yes. So the theory shows that the special case game is unique. The Nash equilibrium of this special game is unique, which is also global optimal, and be achieved by this kind of alternate best response plays. So this is a good news, which basically means that under the special case, we assume there's no background traffic. Well, this is not so true, but you can see that if the content provider's traffic is increasing on the internet, then this is somehow a trend that goes towards this assumption.
Wait a second. It's the opposite, right? It's mostly background traffic. No one content provider is going to have the bulk of the traffic on ISP.
Yeah. No one single content provider. That's true. Yeah.
So a related point there, actually, doesn't seem like a single content provider can significantly drive up a backbone link utilization?
Though that might be the case that when the ISP deploys the content services on its own. So in this case, it may have the separate backbones. So in the separate backbone, if there's routing problems and also these content delivery problems, in that case, the content traffic will constitute the all of the traffic.
So unless you go to like 80-90% link utilization, your delay function at this time scale is essentially flat.
Yes. So it can be differentiated into two cases. One is when the link is under low utilization, and when the link is at high utilization. Yeah. But also the link delay function not always depends on the load, but also depends on the location. In some cases, the link may have a very large propagation delay, and that is exactly the difference between the objective functions between ISPs and content providers. So actually, this theoretical model shows that. So what happens when the objective function is similar, and what happens when the objective functions are dissimilar, and what bad things may happen. Yeah, this is the starting point of this research. Okay. So I assume that ISP and CP have the same cost function here in this special case. Well, this is partially true because sometimes the low utilization may mean low delay and vice versa. But in some cases it's not, because when some link may have very large propagation delay, ISPs probably won't care, but the content providers will care about that. So this theorem has the implication that if these assumptions is held true, then there's no need for coordinate control. By doing this, it is good.
I don't quite understand the no background traffic. Was that an assumption on the previous?
In the previous,
I guess because you're just saying there's one other.
Oh, this is assumption of this theorem, which shows that when their objective function is the same. So here.
I got the function the same part.
Yeah.
Where's the part about no background traffic?
So no background traffic means here, the cost function is the variable of the total traffic on the link. So if there's background traffic, then this objective function for the content provider will not be a function of the total link on the. It may be a function of its own traffic. So that's why we need there's no background traffic there.
Care about the other traffic and doesn't
Yes, no other traffic. Yeah. In fact, it has, but yeah, we're just trying to explore what is the upper bound you can achieve. This is something that theorem tells you.
Can you just subtract the background traffic from the link capacity and assume that the link has a lower capacity?
If you can do this kind of
In a static way.
no, because all these traffic share the link, so they share the same queue. So essentially, they interact with each other, unless you do this kind of physical division. Yeah, like you have these kind of separate backbones, right? So the first, now after the good news is bad news. The first bad news is about the paradox of extra information. So this information basically is that when the content provider is given more visibility, it is not guaranteed to do better. So think about it. In the difference of the CP's model in Model 1 and Model 2 is that in Model 2, it has complete information and it can solve the optimization problem fully solve the problem. But this information tells you that in that case, although it seems that you can fully solve the problem, you're not guaranteed to do better. And here I'm going to show you why this bad scenario can happen. So here I'm just using a simple example to illustrate the high-level ideas about the paradox. So think about, so there are two servers in the on the CP's network. So the user can either choose this server or do load balancing. And there are two background flows from this A to D and A to E here. So for each of these source-destination pair, either the background or the content provider's traffic, it has the ability to go through two links bolded here. Okay, like from B to F, it goes BD or BE. Okay, so we assume that the 4 links bolded here are bottleneck links. So we don't care about the delays on the 4 links here. This is just a toy example I set to illustrate anomalies. So now suppose the 2 links CE and BD here have large propagation delay, which is the CP tries to avoid because it cares about delay, but ISP only cares about the utilization. So in this case, when ISP solves the TE, it is trying to do the work that all links will have the same utilization. Okay? And the server selection is trying to minimize delay, so it should somehow avoid using links BD and CE because it has high propagation delay. Now, consider the equilibrium points of the 2 models. So we say that the paradox may happen when the traffic engineering assigns more CP traffic to the 2 links with high propagation delay. Because essentially, the ISP don't care about may not be caring about the user perceived delay, but if it more cares about the link utilization, so it has a way to arbitrarily assign the background traffic and CP traffic on the links, as long as the links is low utilized, like in this case. So the paradox happens when in Model 2, the ISP unfortunately assigns more CP traffic to the bad links. So in this case, no matter how the CP wants to optimize its network, and it solves the problem fully, it cannot get a better performance than Model 1. If in Model 1, ISP is clever by assigning less CP traffic to the 2 bad links. Yes?
So here you construct this paradox by using assigning larger propagation delay to 2 links.
Yeah.
However, propagation delay was not even modeled in 2 models.
The propagation delay is concluded in the delay function. So the delay function is a function of the total traffic, which, from theoretical model, it may include the queuing delay and the propagation delay.
So where is the propagation delay reflected?
It's in the D function, the delay function. Yeah. So the cost function of G and H may be different in this sense.
ISP in North America would have a 60 millisecond delay from any point, say from Miami to Seattle, in the worst case. So are we talking about those kind of delays?
Yeah, the propagation delay, it depends on, as you say, the propagation delay is something you cannot control, right? It's just this. Yeah, but if you care, but sometimes the queuing delay may be comparable to the propagation delay, depending on how loaded the link is. Yeah. Also, the second bad news is about this suboptimality. So this picture shows the bad news. So think about here, in Model 1, Model 2, so these are the equilibrium points of Model 1, Model 2. But if you characterize the all possible operating region between ISP and CP, here is the whole operating region. And this is the Pareto curve, which means that you cannot improve one dimension further without hurting another dimension. So this is the Pareto curve. So in this case, you see that the Nash equilibrium is not operating here on the Pareto curve. So there exists some space to get further improvement. So this is the second bad issue we want to address. So now we're trying to have a joint design and which addresses the above problems. So before talking about the real joint design model, so we have 2 approaches. One is that we have this kind of oracle model, which is like we optimize everything in the black box. And we blur the boundary of different layers. So all the problems are solved at once. And the information should be shared in the two parties. And they can arbitrarily trade off between two objectives because it is a black box. And you can arbitrarily control the trade-off between the two objectives because you can control the whole decision space. So this is the first model, like this. And second model is like a modularized design. You still want to have separate modules, with one soft TE, one soft SS. So you still allow a layered solution, but with some information exchange. And although you cannot arbitrarily trade off between two objectives, you want to have a fair division of the benefits. And potentially, you can allow the cooperation between two different business entities because it's not getting together. So this is the model we're working for. So the high-level idea of using this joint design is to use this solution concept called Nash bargaining solution. So suppose this is the equilibrium point, which is status quo, which is the equilibrium point of the model 1, which is what may end up today. And there's another point on the Pareto curve. And this solution concept tries to find out this solution. So which is maximize the product of the improvement by the two parties here. So this is the high-level solution concept. So there's some engineering implications. Now, first of all, this somehow ensures fairness because this solution concept is derived from the bargaining process between two players. So it ensures some fairness between two objectives. And secondly, this solution is decomposable, so you can allow for layered decision, which means that you allow one TE problem and one SS problem, which is, of course, the new TE and new SS problem, but with some information exchange between the two modules. And there's no need to explore a large weight parameter space, which means that otherwise it's hard to trade off between the two objectives, which one is more important. And this solution can apply to varying traffic matrix and user demands. Otherwise, you have to tune different weight parameters for different input. So this is the implications of this solution concept. Yes?
How do you define the fairness in that?
So fairness here, well, I don't have a quantitative measure of the fairness, but the notion of fairness is derived from how the Nash bargaining solution is derived. But probably for the sake of time, I have no time to fully derive the solution, but just give you some information that the fairness is derived from the bargaining. Okay. Yeah, if you're interested, I have some backup slides where we can discuss offline. So as I say, the solution concept is derived from these following four properties of the Nash bargaining solution. But I think I don't have time to go through this one by one. And then I'm going to show some evaluation results. So I have some numerical simulations that on these realistic ISP topologies, giving this delay, user demand, and background traffic model, just to realize the more realistic settings of the network. So the first result shows what is the impact of the content provider's traffic on the network. So it is interesting to see that, so in this setting, we fix the total amount of traffic, which is the CP's traffic and background traffic. We fix the total amount. Then we adjust the percentage of the CP traffic, as here, from no CP traffic to 100% CP traffic. Then we measure the performance of the SS and the TE cost. We see that as there are more CP traffic injecting into the network, both of the two performances first seemingly to improve, then degrades again. Okay. So this is an interesting observation, which means that, okay, it seems that if you are running the two problems separately, somehow if there are more CP traffic, you're getting better. But when there are too much CP traffic, this kind of separate models will do worse again. So the reason is that for if we look at the traffic engineering cost, so if we have more CP traffic, so it means that you have a higher possibility to find some closer by servers, so without going long links. So that naturally decrease the link cost here because you're using less links. But where there are more CP traffic, that means that the conflicting objectives of the two parties is really a problem because of the interaction. So because they're conflicting objectives, then the performance goes up again. So this is the cause for this kind of curve. Okay, so there are some similar reasons for from the CP's point of view. So first of all, when there are very little traffic, there's nothing much you can do because the ISP always allocate your traffic to some bad links with large propagation delay. There's nothing much you can do. But if you have larger share, the ISP cares about the link utilization. Then it has a better chance to put you to better links. Okay, and when there are more CP's traffic, then in this case, because the conflicting goals between the two parties, then it worsens the performance. So of course here, the performance is the average delay for the content provider. So it has nothing to do with the actual amount of the CP's traffic.
This is basic here. Like the up part doesn't surprise me. The more traffic you put in, the more it's going to cost for both of them. Right?
No. Here I fixed the total amount of traffic. The total amount of traffic is the same.
Total amount being like background plus.
Yeah, yeah.
Oh, okay.
But I just vary the percentage of the traffic.
Oh.
Yeah.
So it's happening because the content provider traffic is non-uniform and the background is uniform. So we don't then assume uniform capacity everywhere. So
it's not uniform.
So I guess the links have uniform capacity.
Yeah, yeah. This is.
And the background traffic is uniform. Is that right?
Uniform.
I'm also trying to understand the rise.
The background traffic. What do you mean by uniform?
So I guess
you're
no. Charging for the worst link getting heavy, and so the reason it would go up is somehow there are a few links, maybe one or two, that get a lot of the traffic. Right? That's what's happening when the cost is high. So there must be you're focusing more traffic on a few links when there's a large percentage of CP traffic. So there's a few hot links. Is that right?
Yes, there's a few hot links, but in the simulation model, the background traffic is not uniform. So I just randomly pick up some assign. It's a random, yeah.
Random but unbiased.
Yeah, unbiased.
Is there a server at every ISP pub?
Every ISP.
How do you choose the server locations?
The server is randomly chosen. Yeah.
They're not present in all pubs.
Not what?
And they're not present in all nodes of the ISP.
The server is not present at every node of the ISP, but it's randomly selected. A subset.
And what about the value of the demands?
The value of the demand?
For the content provider?
You mean the user demand?
Yes.
Okay. It is so it is chosen to reflect the network load. So as I say, I fixed the total amount of traffic. Okay. So I simulate some scenarios when the network is lightly loaded or heavily loaded. So given the capacities, I'm trying to first figure out what is the total demand. Then I just assign the user demand according to the percentage of this traffic.
Follow some distribution or some statistical distribution or
for all the user demand?
Yes.
It's just the user demand is uniform. Yeah, user demand is uniform. Yes.
Can you
remind me what is SS cost and what is T cost?
T cost is just the link cost. It's the sum of the link cost function. No, the T's link cost function is this kind of convex shape curve, as I showed you earlier, to reflect the link utilization. But for the SS cost, it is the sum. In the model, I use this MM1 delay model and plus the propagation delay. Yeah.
If you have, like, let's say two content provider traffic, so let's say one is taking 20%, the other is taking 80%, right?
Mm-hmm.
So I mean, both will have a similar curve, right? But then when you add the two up, it seems like the total, I mean, link utilization should be constant, right? If you add, let's say, if you have two content providers, so both have a similar curve, right? But
Two content providers. So in this setting, there's only one content provider.
But I'm saying, like, if you had two content providers, then I mean, it seems like the total utilization should be constant, right? Because you said the total traffic is constant, right? It's just the percentage between one provider and the other provider keeps changing, right? But it doesn't seem like that would be the case. It seems like the total link utilization would be higher when there's a larger skew between the two content providers.
Yeah, so intuitively, yeah, it's true, like, because the total demand is the same, right. So the utilization is the same.
But it seems like when there's a larger skew between the two content providers, the link utilization is higher, but the cost is lower. Okay.
Because I haven't seen, well, if there are more content providers, there may be self-interaction between the content providers, which is not reflected here. So.
You mentioned this oracle model, right? So if you were to plot the oracle here, where would they be?
Oracle is like, because in oracle you can give different weights to the here. So in that case, it's hard to say how you can assign a weight. So that is why I go for the second model, the modularized design. Yeah. Okay, so let me quickly go through other results. So this result shows performance improvement over these models, over model 1. So the yellow bar refers to the improvement of model 2, and green is the model 3. So we see that when the network is under low utilization, somehow the model 3 is doing better than model 2. And the high improvement occurs at the two extremes, when there are less CP traffic or more CP traffic. So this is the general trend for this model. There's some improvement, but sometimes the improvement is very not significant. Like this is the percentage of the improvement. Okay, so this is under low utilization, when the link is always spare. So you can see, because if link is under low utilization, there's nothing much you can improve. But if the network is under high utilization, then the improvement somehow can be very significant. Like in this case, can be like here, 80%. And also you observe from the simulation that this kind of the paradox of extra information can happen, which means that the model 2 will not improve, as reflected in here. So this is to see the improvement of the two models. Yeah, so I also carry out some other studies in various topologies. Yeah, I think I'll skip this one. So the main goal of this job is to see the forest through the trees. So now the coexistence of the ISP and the content providers is a hot discussed topic. And there can be many models, like cooperation models, like the P4P working group. People there are proposing the cooperation between peer-to-peer and ISP. So here, it's just a table that reflects the possible changes to the two players. So either one changed or two both changed, or only one of them changed. So this work characterized the three entries here and show their performances and how much work you have to do to migrate to these models. So for the conclusion of this first piece, sorry, I'm running a little more time. So this is the conclusion. So first of all, this is a first step to study this problem. And I just tried to propose a solution concept that can give you some insight into which is the right approach to go. And I also, another contribution of this work is to provide another analytical framework to study these pros and cons of these models. So before going into the second part, which is very, very short, is there any questions?
Is there any related work? Is this the first work in this area?
Yeah, the second work is related to some of my ongoing work, which is also related to the potential problems I'm going to solve in here. So that's why I would like to take a few minutes to talk about that. So I'll go very quickly. So the second part of my work is to characterize the performance metrics in peer-assisted live streaming system and to see how we can monitor the peer's performance in an efficient way. So the goals of my work is to define these formal languages for the performance metrics in peer-assisted streaming system. There are three metrics I'm considering right now. One is rate, another is delay and robustness. So we want to identify what are the system bottlenecks contributing to these metrics from some measurement studies in a real P2P streaming system. So this is some of my work I was doing in the summer. Then my goal is to build some models to quantify these metrics, and then how to optimize these metrics and trade off them through the possible design variables. And finally, to provide this algorithm design and protocol implementation. So the first one is about the rate limitation. So this is the collaboration work with another postdoc in my group. So in this work, we are trying to characterize the performance bound for the rate. So in this study, we model the live streaming as either tree-based streaming or mesh-based streaming as a multi-tree construction. Because essentially, for every bundle of the stream, it goes to each of the peer, and these bundles actually spans over all the peers, so it forms a spanning tree. So for different bundles of the stream, it can go through different spanning trees. So we're trying to answer the question, so what is the maximum streaming rate given the capacities of all the peers? And the second problem is, if you want to achieve the desired streaming rate, so what is the minimum server capacity you need to achieve this? So the two problems are actually dual problem, prime and dual problems of each other. And third, if we're going to build these trees, what is the minimum tree depth we can guarantee? So in our, this is our past work. So we answered the three questions in these dimensions. One is that we don't have degree bound for the peers. So for each peer, it can have as many children as possible. And second case is that for one peer, it can only have one child. So this is another case. This is the second scenario we consider. And the third scenario is that we can have arbitrary fan-out degree, but we assume that the users are homogeneous, like they have the same capacity. And the last case is they don't have the same capacity. They're heterogeneous users. So the second problem and third problem is what we solved in one of our prior work here, which appeared in Symmetrics last year. So we either give the bound, we both give the bound and how to achieve this bound by constructing these trees. So this is the work we're doing to quantify the rate performance. Another work we do is to quantify the delay metrics. So this is really from the user perceived delay, which includes the startup delay and playback delay. So we differentiate the different components that constitute a delay by categorizing them into different groups, like the link delay, node delay, and processing delay. And then we give a set of the design variables here. Like in the P2P streaming, we can control the chunk size, we can control the fan out and tree depths, streaming rate, and the tolerable loss rate, and the pairwise peer capacity and signaling method. So we try to answer the question with these design variables that we can control, and how can we optimize this matrix. So this is one of the tables that so we discuss to give the importance of these design variables to each of the components that contributes to the total delay. So in here, the more stars means the more significance to the total delay. So we also have some simple analytical models to quantify these performance metrics. So this is the high-level picture of what I'm trying to do in the future. So another component of my work is the P2P traffic measurement of a real tree-based live streaming system. So in this work, we collect the logs from each of the participating peers. And by using these logs, we're trying to quantify the user performance and find out the system bottlenecks. So to find out whether these our assumptions about our models is correct. So this is to verify our models by using these measurement data. So like here is a high-level picture of what I obtained from the measurement study. So like here, if we think about a tree-based streaming system, if this is the overlay tree depth, and the y-axis is the delay, so we can see that the delay grows proportionally somehow to the total delay. So this is the case in the real operating P2P system when there is no IP multicast support. But when there's IP multicast support, we can see that the delay is somehow not so significant distinct. Because in this case, if you're using multicast, the data is not really transferred through the trees. So there has some possibility that even if you have high tree depth, the delay is comparable to compared to the nodes with the low depths. So this is the improvement of the IP multicast scheme in their operational system. So this is part of the study I've conducted. So this is all of my talk. Any questions?
So the multicast support for the meant that you could multicast to your neighbors?
It's
in
not
the overlay tree? I mean,
no, it's like so you can detect a possible set of the peers are within the same like IP multicast capable domain, like in the same LAN. So in that case, they will open the multicast option. So the data actually go through the multicast tree rather than go through the overlay tree.
yeah. So, yeah, I'm trying to understand. You've got an overlay tree.
Yeah.
So every node has some neighbors in the overlay network. And that means you're only going to communicate with those guys, the neighbors in your overlay network, but you can do so through IP multicast? Is that what?
So.
I mean, or can you IP multicast to the entire, you know?
Oh, I see. So.
In which case, what purpose does the overlay serve?
Okay, so the control path of the IP multicast is not exactly the same on the overlay tree. So the overlay tree is only responsible for the data streaming on the traditional tree-based multicast. But for the IP multicast, they have their own control group, so they can discover like which of the peer neighbors are on the same multicast domain. So they are not communicated through the overlay tree. So that's why you have a possibility to find out more possible candidates rather than just your overlay neighbors.
Yeah, but that means some of the links in the overlay tree are not actually used for streaming data because data is already broadcasted in the underlying.
Yeah, that's true.
So what purpose does the overlay serve?
So overlay serves when the IP multicast. Well, first of all, when it's not possible. Okay, because in most cases, if it's in wide area network, the IP multicast is not possible.
Okay.
Yeah, so that is.
So you use it wherever you can, basically.
Yeah, it's just there the design principle.
I guess you like have an overlay tree, but instead of like the information passing down through the tree, it might just show up in very like other nodes within the tree at the same time. I mean, is that right? I mean, you don't need to wait for it to flow down the tree; it just comes through it.
So before they decide whether the data is streamed through the overlay tree, so they first would detect whether it is possible to do this IP multicast. Now, of course, some of the nodes are still getting the data from the overlay tree. But let's say this head on the overlay tree will serve as the head of in the IP multicast. So it is still getting the data from the overlay tree, but it forwards the data to its descendants through the IP multicast. So it's a combined mechanism of the two approaches. Other questions or comments?
So, I think the interaction between the traffic engineering and then the content provider is a pretty interesting topic. Mm-hmm. But I wonder whether it's possible to make the objective function of the content providers more realistic. So like say, if the performance, you care is delay, right? So
yeah.
You don't necessarily want the lowest delay, right? For example, Akamai doesn't route the clients to the closest guy. They just route clients to good enough guys.
Yeah, good enough guys.
Okay.
And possibly some.
So that's for delay. For throughput, it's the same thing, right? So if I'm content provider delivering Netflix, I only have a few rates, 1 Mbps, 2 Mbps, right? So 1.5 doesn't mean too much for me, right? So I can either do 1 or 2.
Yeah.
Or and I probably don't have anything beyond 2. Right?
Yeah, you don't really care about. But sometimes you don't really care about delay, like it's not delay sensitive traffic, like it's just video.
Right. Yeah. So just thinking this COMEX type of cost function, not exactly modeling what the content providers really care.
Yeah. So in here, we use the delay function is somehow also convex. So we use the MM1 model, but in fact, so. There can be, as you say, there can be different user cost functions assigned to each link, which can either be also depends on whether the cost can be additive. Because sometimes, if it's not additive, then this model does not apply. I think this model applies to additive cost. Then you can give different, of course, you can give different shapes to the cost function. But in here, I'm just trying to show what happens if the cost shape is quite similar. Because in here, the cost function of the ISP and the CP is quite similar. And we try to answer the question, even in this case, what are the possible anomalies and efficiency loss? Then, of course, in reality, there can be quite different objective functions of CP and ISP. But in that case, maybe the gap, optimality gap will be larger. So I think by using the same cost function, well, quite similar cost function, I'm just trying to show give some insight into these kind of interaction and what will happen.
I guess to follow up on that theme, I was thinking about is that, this is a competitive environment. Did you model, in any case, the real costs or 95% all charging or anything related to how content providers really do relate to ISPs?
You mean thinking about some economics cost.
Right, I mean, they signal back, their bargaining happens with dollars.
Right, that's true. So here, I'm directly transferring the performance into dollars. But if you think about the real dollars, so in that case, you should really consider multiple content providers because they can offer different contracts to the ISP. Say how much capacity I want to guarantee for this. Yeah, that's a very interesting problem to study. In that case, you also need to consider this kind of inner ISP policies, like in that case, because some ISP want to attract more traffic, while some ISP don't free ride the traffic, don't want some traffic to free ride without getting any revenue. Thanks.
Okay, thanks for the excellent talk.